Hello everyone, welcome back to another class on regeneration biology, and today we will learn different steps in tissue engineering. And so far we have seen the importance of tissue engineering, how it is done, its pros and cons, its ethical implications, etc. So today we will learn about what are the steps. Steps means not exactly the methodology. Some methodology angles also we will touch it, but we will try to understand the overview. So tissue engineering is a multi-step process, and it includes the cell isolation, scaffold creation, cell seeding, and tissue growth stimulation, and ultimately leading to the creation of functional tissue for transplantation or other applications. So this is the overall theme of tissue engineering, or the flow chart, or the what you call it is the workflow of tissue engineering is this, as it mentioned. So a commonly applied definition of tissue engineering by Langer and Vacanti, the pioneers in tissue engineering field, is an interdisciplinary field that applies the principles of engineering and life sciences towards the development of biological substitutes that restore, maintain, or improve the biological tissue function or a whole organism. So this is the definition by Langer and Vacanti. And in addition, the same researchers, Langer and Vacanti, also state that there are three main types of tissue engineering. One is cells, tissue inducing substances, and cells plus matrix approach, often referred to as the scaffold. And tissue engineering has been defined as the understanding the principles of tissue growth and applying this procedure to functional replacement of tissue for clinical use. So you need to have cells to start with, and then that cell has to become a tissue so that a function can be delivered, or you should have the cells with a scaffold on which the cells can be forced to grow and then allow them to differentiate, so that you can transplant this artificially made tissue. So either make on the site or you make somewhere else and bring onto the site. So this is the simple approaches. Another description says about tissue engineering, underlying supposition of tissue engineering is that the employment of natural biology of the system will allow for greater success in developing therapeutic strategies aimed at replacement, repair, maintenance, or enhancement of tissue function. Another approach, or the another definition of tissue engineering. So you may wonder why different definitions are important, because the whole concept of tissue engineering itself will be unclear unless the definition or the approach is not well defined. It is very much vulnerable for getting diverted into a obscure area, or not so significant area, and it can get diluted off. Many such disciplines have got into that trouble. That's why defining a proper disciplinary area is very, very important. So developments in the multidisciplinary field of tissue engineering have yielded a novel set of tissue replacement parts and implementation strategies. Scientific advances in biomaterials, which is basically you use a scaffold, and also stem cells. Stem cells means stem cells are stem cells, but understanding them, how to tweak them to differentiate into a given direction. So these are all the understanding the stem cells, means not learning their biology, but learning how we can convert them into a multi-cell type tissue derived from a given stem cell. So growth and differentiation factors and biomimetic environments have created unique opportunities to fabricate or improve existing tissues in the laboratory, from combinations of engineered extracellular matrices, which we call it as scaffolds, cells, and biologically active molecules. So sometimes this newly formed tissue have got a future way if they are assembled properly. Otherwise it will get disassembled and it will get fall apart. So it is very important to follow up how good you are going to retain the stem cells properties with all its biological qualities so that you can push them into a tissue in a defined environment. Not that I wanted to make a cardiac tissue and this time it became a liver tissue, or I wanted to make a liver tissue and this time it became a kidney tissue. You don't want that to happen. Among the major challenges now facing tissue engineering is the need for more complex functionality, biochemical stability, and vascularization in laboratory ground tissues destined for transplantation. This I have discussed many times, that if the newly formed tissue doesn't have a future, now it has a future because you are providing the medium. But once it is put into the organism is supplying blood, but the blood and oxygen is not reaching the newly formed tissue. How it can reach? Because no tissues will be stable if it is exposed to blood directly, because we have closed circulatory system. It should gel well with the blood circulatory system. The angiogenesis of the newly formed tissue is very, very important, as important as the tissue itself. If someone asks, is the tissue important or is blood vasculature is important, I would say blood vasculature is important, simply because tissue has no fate if the blood vasculature is not properly made. So the basic procedure of artificial tissue preparation. Tissue engineering is an interdisciplinary field that applies biology and engineering principle to develop biological functional replacement. This we have seen it, and it is used exclusively in the clinical application. It offers the possibility of helping regenerate damaged tissues by trauma or disease. You can get a damage to a given tissue by multiple means. It can be an infection, it can be a mechanical damage, it can be trauma, etc., or it can be a genetic disease also. Creating new tissues and replacing or of the failed tissue or failing tissue or malfunctioning organ. So that is the overall theme of tissue engineering. So tissue engineering includes prosthetic or artificial replacement of the tissue, and it can be replacement of a part of the tissue or a entire organ itself via organ transplantation, and maybe a selected area of that organ also you can get transplanted. Say for example, if you're doing a liver transplantation, you don't need to make an entire 1.5 kilo size liver. You can make a 10%, around 100 gram of tissue, you can put it. It will grow back and become a normal liver. So that is the overall theme of the transplantation of the artificially made tissues. Artificial tissues include artificial pancreas, artificial bladder, skin, bone marrow, oral mucosa. These all can be made by tissue engineering, and the list continues. These are all not the only tissue. These are all used extensively for various clinical application. So let us look into the detailed breakdown of these steps. Cell sources and isolation. Identifying the appropriate cell type. The first step is to determine which cells are needed to regenerate the desired tissue. Say you decided to go for a vacation. So the first thing you need to know is that what is my destination. Then only everything else comes into picture. How I will go there, do I have the money, who all will go, how many days I will stay. Everything can be worked out if you know the destination. So cells has to be identified, cell source and from where I will get it. And then comes the cell isolation. Cells are obtained from the patient, that is basically they are autologous cells. A donor, which won't be autologous, but what if this patient doesn't have the cells to donate? Say someone's pancreas is failing, where from I'll get pancreatic cells from him? Of course I can make stem cell from him or her, and then convert them into pancreas. But it would be nice if I can get the pancreatic cell itself so that I can make the organ without too much of a problem. And can be derived from the stem cells also, as I mentioned just now. It can be from the iPSC cells from the patient. But these are all adds to the cost of the production. Every step when you are going back, then it adds to the cost. Cell expansion and differentiation. The isolated cells are cultured and if necessary induced to differentiate into specific cell type required for engineered tissue. So you should be able to convert X into Y or stem cell into that Y tissue. And scaffold design and fabrication. So next part is, okay, I have isolated the cells, I know how to differentiate, everything is there, but now I want a particular shape cell because that is what I am using for transplanting. Then you need to have a particular shaped scaffold. on which you will colonize these cells. Scaffold material selection is very important. A suitable scaffold material is chosen based on the type of tissue being engineered, considering factors like biocompatibility, biodegradability, and mechanical properties. All these things comes into picture. And scaffold fabrication. The scaffold is fabricated using various techniques, including 3D printing, electro spinning, or other methods to create porous three-dimensional structure. So why porous? Because then only cells can move across. Then only the medium can go between the pores. Everything is important. Then comes the seeding and tissue growth. Seeding means basically inoculation. You may have seen how your mother or anyone in the family taking a curd and putting into the milk, and that is nothing but inoculation. Like that you have to do the seeding. Cell seeding. The isolated cells are seeded onto the prepared scaffold. You are putting into the scaffold. And then culturing and stimulation. Culturing means they should get the medium. The scaffold cell construct is cultured in a controlled environment, often using the so-called bioreactors to promote the cell growth, differentiation, and tissue promotion. So you are stimulating the cultured cells on a scaffold now to differentiate, again by controlling the medium. You change the contents of the medium, say C2C12 cells, myoblast cells. If you put say 2% horse serum, they can become more differentiated, and they can even start twitching in a petri dish. They can become contractile muscles. So growth factors and signaling molecules. So the growth factors always contribute for their maintenance, survival, and progression. Signaling molecules, growth factors and other signaling molecules may be added to the culture medium to stimulate cell proliferation, differentiation, and tissue organization. Like C2C12 cells, they are not used for any organ transplant, but they are the muscle cell line. You can make them to differentiate into muscle fibers just by putting horse serum. Instead of bovine serum albumin, you put a horse serum, it will differentiate. There are different, one example I am telling. So tissue engineering and its implantation. Say you made a differentiated tissue on the scaffold, everything has been done. Now the tissue formation, the cells that proliferate on the scaffold and interact with the scaffold, they form new tissue structure. That is, the scaffold's shape is the tissue's shape. So then comes the implantation. The engineered tissue construct is then implanted into the patient's body, integrating with the surrounding tissue and performing its intended function. Then you can tell this is completed, or the one circle is completed, starting from cell into transplantation. Until that stage it is done. Now let us see the steps to prepare artificial tissue science, artificial tissue, which is the science methodology of this artificial tissue. The tissue engineering procedure involves several steps, which starts from cell selection, cell isolation, and culturing of the primary progenitor or stem cells, and inducing their differentiation to certain phenotypes, seeding and cultivation, design of adequate scaffolds, including selection of proper materials and routes to process, porosity of the scaffold, interconnectivity, surface characteristics. Everything matters, because the newly formed tissue is only as good as the scaffold, or whatever you started with, that quality only will be there. It's like there is a popular saying, if you put dirty water on your head, when it comes to your feet, it is not going to become pure, it is going to become more dirty. So it is very important that you are starting off taking which scaffold, or what is the shape of the scaffold, and what is the cell I am using for seeding. Everything contributes to the final success of the tissue production. Let us see the stepwise procedure. First, you start with the biopsy. Biopsy, all of you would have heard about it. That is one way of accessing cells from a tissue to test the cancer. So biopsy is basically donor tissue extraction, either from fluid tissue like blood using centrifugation, or apheresis. That is, it's an easier process. You can get it, concentrate the cells, or from a solid tissue that involves more steps, like needle biopsy people take with a needle, etc. Solid tissue is minced, then enzymes like trypsin or collagenase are used to remove extracellular matrix. Finally, cells are free floating and extracted using centrifugation or apheresis. So you first dislodge cells by trypsinization or any other protease treatment. Trypsin, because it can selectively cleave the matrix protein, and you will get individual cell suspension, and you spin it, concentrate it, and you get the cells. So lately, the trend in donor tissue extraction is to emphasize more into a non-invasive method. So people, if the organ is very vital, I want some cardiac tissue, I don't want to make a pinhole in my heart, which can invite more trouble. So there are much easier methods are being developed these days. Cell isolation and cultivation. Manipulation with cells. It is the safest to use autologous cells, that is primary cells extracted from same person's healthy tissue to which artificial tissue will be transplanted. Recently, there have been a trend to use mesenchymal stem cells from bone marrow that can differentiate into various tissue types. Other types of cells that can be used are allogenic, that is a donor from the same species, like person A donating to person B. Both are Homo sapiens, that is allogenic, and heterologous, that is, or xenogenic, that means donor is a different species. Donor can come from a different species. In those cases, rejection of host's immune system and possible disease transmission is there. But when you are not getting a donor, then xenogenic becomes attractive, and the risks must be considered, because every topic, every situation has got its own pros and cons. So if you look the scaffolds and seeding and cultivation, implantation or seeding of cells into artificial structure that can support 3D tissue formation and that resemble the extracellular matrix. So this is one approach that is extensively used, and there are certain requirements that scaffolds need to meet. What are they? Biocompatibility, that is acceptable for cells, high porosity and adequate pore size. These are biocompatibility is an important criteria. Then comes biodegradability. Biocompatibility means it should not raise an immune response in the host, and it should degrade off also, that later it will be replaced by the extracellular matrix released by the cells grown on the scaffold. And non-brittle nature, that means if it is brittle, this scaffold or this tissue will break easily, so you don't want them to be brittle. And it is preferable for scaffold to be absorbed by the surrounding tissue, that it will vanish into thin air. That is what is most expected. Can be functionalized with biomolecules, and they can function as nutrition for cells. Sometimes, think about the situation, while the scaffold is degrading, it acts as a nutrition for the cells. So there are such approaches are also being considered, and all these adequate properties must be present in this scaffold so that the formed tissue will be ideal. And implantation, that is implantation into the living body, and then detection, that is basically called the property analysis. That means I put a tissue, okay, it is staying there, is it doing the job? We have to see the end product as the function of that organ. Say if you made a liver tissue, it should produce the liver enzymes, then only it has a meaning. If you look closely, an overview of tissue engineering, you can see there is a novel cell sources and tissue architecture techniques, and iPSCs are there, and reprogrammed cells are there. Cell culture in vitro, they can be made into bioreactor, and you can make them into whatever tissue you want by growth factor, transcription factors, and you can give different types of stimulus onto these cells so that they can be made into a proper organ part on those various engineered materials. And this engineered tissue, when it is ready, let it be anything, like sometimes people use a decellularized organs also. It's like you take an organ, say heart, and get rid of, say I took a pig's heart or a buffalo or any other animal's heart, and I removed all the cells, but I'm using the matrix of that organ, now allows the cell to colonize. I don't need to make any difficulty, or I don't need to face any difficulty, because the shape is already there in the matrix form. The cells will colonize and it will look like a heart, particular heart shaped structure. And people also use 3D bioprinting these days, so that you can scan the dimension of an organ and you use cells to print into a proper organ. And final implantation and validation of the organ's function. Now, tissue culture is also, this organ also is used for some interesting other projects. So this is called a tissue culture art project. So while it is called art, it has got a lot of artistic viewpoint. It's an ongoing research and development project that is initiated in 1996, was set to explore the use of tissue technologies as a medium for artistic expression. Some of their projects are, one is a semi-living worry doll H, and victimless leather, a prototype to stitchless jacket grown in a techno-scientific body, and semi-living steak 2000. So let us see some examples. So this is semi-living worry doll. So it was created in 2001 by Oron Katz and Einat Zur and Guy Ben Eri. So these three scientists, they created it. The semi-living worry doll is a project that reinterprets the story of the Guatemalan worry doll to deal with contemporary anxieties. If you have this doll with you, you will not deal with anxiety, and it's made of living meat, as you can see in this picture, in a petri dish, and it's a doll. And people find it, this is the artistic view. Another example is victimless leather. If you are wearing a leather jacket, you have a feeling, oh, this is a skin of some animal and I killed it. Or I'm wearing some leftover of a dead body, those kind of feelings. So these days you may have seen in mobile phones, people say, oh, we are using vegan leather. So vegan leather means it's an artificial leather, but it is, no animal is hurt or harmed. So this is something called victimless leather, made in 2004, a prototype of stitchless jacket. The good thing is, if you can culture cells and then you will not have any stitches, because normally any leather jacket, you make pieces and you stitch it. You don't have to stitch it. It will be stitchless leather, and grown from cell culture into a layer of tissue supported by a coat shaped polymer layer. On top of that, the scaffold is like shape of a coat, and in that you are allowing the cells to grow. It is grown inside a bioreactor that acts as a surrogate body. As you can see here, medium is been given, every conditions are maintained, and you end up getting this jacket, as you can see here. The artistic grown garment is intended to confront people with the moral implications of wearing parts of dead animals for protective and aesthetic reasons, that confronts notions of relationships with the manipulated living system. Some people may, oh, why I should carry a part from a dead body of another animal. These are all some thoughts people can have, and that can be overcome by this kind of approaches. So another option you can see is semi-living steak. So here what it has been done is, in 2000, the first steaks measuring around 1 centimeter in diameter were composed of prenatal skeletal muscle cells. So what they did was, they took a small piece. Steak means, which people eat as a food. So around 1 centimeter in diameter, they took that was composed of prenatal skeletal muscle cells. So from an embryo, you took the skeletal muscle cells taken from an unborn sheep. Sheep's skeletal muscle cells are taken, which were then seeded on a degradable matrix. So skeletal muscles are growing onto that matrix, which is basically scaffold. And the semi-living steak was the outcome of a residency at the Tissue Engineering and Organ Fabrication Laboratory at a Harvard Medical School in 2000. So the semi-living steak is the first known proof of concept for using tissue culture exclusively for food. We should understand, in future, it is very much likely that people will run short of natural resources for satisfying the need of natural resources as a food material. If number of people are up to certain threshold, you will be able to provide them from the nature itself. like there is a saying, right? There is enough in the nature to satisfy the need, but there is not enough to satisfy the greed. Same way, the food, when the number of people consuming food goes way too high, then food will come under the category of greed, although it is a need. So that time you might have to come up with strategies to make, those who are non-vegetarians, or even probably for that matter, even if they are vegetarians, you should come up with artificially making. One is a plant tissue, another is an animal tissue. That is the difference between vegetarian versus non-vegetarian. But without killing an animal, if you want to have the feeling of having non-vegetarian food, people are also exploring the possibilities of, I think it's already out there, people are putting collagen gene, which is an extracellular matrix protein, in potato, and you end up having a non-vegetarian potato. So vegetarians cannot have that because it's a non-vegetarian potato, but it is not from an animal. It is just a gene which is produced in the plant itself. So we are now kind of making the lines thinner, but it has application. Why this is been discussed, like coming back to this semi-living worry doll, you may wonder what is the implication in tissue engineering. Of course it is tissue engineering. Only thing is, you did not use tissue engineering to save the life of a patient. That is the only difference. But tissue engineering, you created a doll which is exactly made of meat, exactly made of flesh. So that is what, it's basically you are satisfying the your this is basically Guatemalan belief of worry dolls. You can read about it. That is used for dealing with contemporary anxiety disorders. And victimless leather also, we discussed that victimless leather also, people want to have the all the qualities and features of a leather. They love leather. That is why I discussed the vegan leathers have come into picture. So it is not for what you call, it is not that uh, people don't like something, but the property of that material, or the way through which, or the means through which you have created a leather, that worries you. Oh, this is from a leftover of a dead body. So this worries people. That's why some people don't use it. So once you know, oh, no animal is, there is no connection with this animal, then your problem is solved. So this is what you should get the idea, that although it is costly, there are people out there who can deal with it, who can take it, and there is no issue whatsoever with that. So that is why, and proof of concept, proof of principle can be done, and it also gives you an idea until where the science can go. So we should understand, while using the technology for doing something, you should also understand that it has got other markets also. Like when Corning Gorilla Glass was discovered, people never knew that it will become, because it was discovered some 1950s, if I am not wrong. That time people did not know, although knew glass will not drop if you drop it, but it never took off because people said it's very costly. Why should if glass breaks, I will buy a new one. But now mobile phones are more costly. Hence, if you drop mobile phone, you don't want the screen to be broken. So that is why after several years, it was ahead of time, the discovery. Same way, this victimless leathers, in future, it may reach a situation, it can become a fashion statement. It may be costly to start with, but it can become cheaper eventually when it becomes popular. Same way, the semi-living stick, which we discussed, although it may sound very trivial, especially when there are plenty of food available out there, but it won't be trivial when that is the only way of getting a food. Okay, so we will learn more about regeneration biology in our next class. Thank you.